Hello everybody. So today I'm going to be showing you how you can prove a statement involving smoothness. So first, I want to remind you of two definitions that have been talked about in other videos. In particular, what a smooth function is, and then what a B-smooth function is. So a complexity function that is asymptotically non-decreasing, and it also satisfies f of 2n is big O of f of n. We call that smooth. Now, you might ask, Dan, what is that useful for? I have a proper video just talking about that. I'll have a link to that in the description if you're watching this or if you're reading about this. This is all part of the same area in my notes. Then there's this other property called B-smooth, which is a stronger property. So it says much more than just this. It means it's asymptotically non-decreasing, and that means that there's a sufficient, so this asymptotically non-decreasing business, remember, this means that there exists a positive integer n0 such that if I plug in f of n, it must be either equal or less than f of n plus 1. So it's allowed to be equal, but it can't be exceeding the next value of n. So f of n is going to be less than or equal to f of n plus 1 for all n greater or equal to this n0. So the goal would be that you'd prove n0 exists. So that's what smooth is. So it has these two properties. B-smooth has the first property, but the second property is a much stronger one. It says that no matter which integer constant you select, so it has to work for every one of these integer constants. So it's 2 or greater, but it's also true for 1, but for 2, oftentimes it's defined as 2, as opposed to just at 1. If b is greater or equal to 2, then it must be that f of bn, where b is the constant, is big O of f of n. So this is what B-smoothness is. So what we're going to do is prove in this video that if f is smooth, then it must be B-smooth. So that's what we're going to prove here. We're going to use mathematical induction to do that. So the first tip I have when writing down a mathematical proof with uses induction is usually denote what you're trying to prove. Like I said, normally we have a game plan that we try to come up with. So we have to have some strategy to help us guide us through the proof. So I'm going to denote what the statement is. So I'm going to perform induction over b in this case. So for any integer b greater or equal to 2, let capital B of lowercase b denote the statement and now this is how I'm going to write it down. So b of b is going to be f of bn is big O of f of n. That's what I'm going to perform induction on. So that's going to be my goal, is to prove this for any one of these b's greater or equal to 2. Now, you might ask, Dan, why aren't you saying anything about the first property? Well, some mathematicians or computer scientists might look at your proof and say, well, that's kind of obvious. Why do you include it? You can include it. I would recommend, if you wanted to, put it at the beginning of the proof. Say, well, any smooth function is eventually is asymptotically non-decreasing, so the only thing that remains to be proven is that we have to prove the second property. That's what you would put right here. At least that's what I would recommend putting it. It makes it easy enough to see what you're trying to do. So you could put that right there if you like. Some people that write proofs out there might say, oh, that's kind of obvious because they're both the same property. But for the sake of board space, I'm not going to put it here, but I would recommend, if you really wanted to be diligent, put it in there. Just in case. But for the purposes here, I think that this is, like, they both have this property. So really, we only care about this. So, what's the first thing you do in an induction proof? Normally you prove the base step. So you might have multiple base steps, but here we're only going to have one. We're going to be proving this using so-called weak induction, or just, you might know this as the principle of mathematical induction. So I'm going to start with b is equal to 2. So I'm going to prove a base step. So I'm going to plug in 2 and see if it's true or not. So I'm just going to plug this in. So I want to prove b of 2, which means that I want to prove that f of 2n is big O of f of n. Well, that's literally the definition of smooth, right? So let's just put that in. Since that says since the microwave sort of melted that one. Since f is smooth, f of 2n is big O of f of n. Proving statement B of 2. Right? We're done the base step, believe it or not. We just used smoothness. We got it for free. Is that wonderful? So now I'm going to prove the induction step. So if you're not familiar with induction, what I'm going to prove for you is that if B of k is true, then it must follow that B of k plus 1 is true. So I'm going to define what k is. So if you're not familiar with induction, I'm going to start off with B. So that's the base step. Now imagine if I give you two arbitrary inputs of B. So I want to show you how you can get from one input of B to the next one, so the next highest one. So I'm going to use statements I know about B of k, where k is going to be some value of that would have been B originally. But it could be arbitrary, as long as it's larger than or equal to 2. So I want to imagine if I gave you B of 2, I want to show you how you could prove that with B of 2 being true, that P of 3 is also true. Okay? So think of it like a ladder. I'm trying to teach a cat to climb a ladder. So if the cat knows how to climb up one ladder, so one rung on the ladder to be more precise, then I'll be able to go all the way up the ladder if I know how to do it with one rung. So that's the idea. So, like I said, I'll be doing a proper video on induction. So keep an eye out for that. So fix some k greater or equal to 2. And assume that B of k, f of kn. Now this is very unfortunate use of variables, but we're going with it anyway. So B of k says that f of k times n is big O of f of n. So we're going to assume this holds. So this is what we would call the induction hypothesis or the inductive hypothesis. Which I'll abbreviate as IH. So I'm going to assume that B of k holds, and I'm going to show you how you get B of k plus 1. So let me move us over. So we will show now that B of k plus 1, the B of k plus 1, so let's just say what that is. So let's say what that is. That's f of k plus 1 times n is big O of f of n. Also holds. So if I could show B of k, it follows from B of k that B of k plus 1 also is true. Then if I plop in like B for whatever value it might be, it'll work no matter what k was in my proof. So I'm using k as opposed to B because I find it a little bit less confusing. It's a pretty standard thing to do with an induction proof. So here's what we're going to do. Function of, so we're going to invoke a property of the function. Function f is asymptotically non-decreasing. It's asymptotically non-decreasing So for sufficiently large, so remember this just means that there exists the n0. So for sufficiently large n, it must be that f of k plus 1 times n, all inside the f here, is less than or equal to f of 2 times kn. So you might ask, where did that come from? That's a matter of intuition for this proof. So notice that k plus 1, if I give you that means that there exists n0 such that this inequality is going to hold because it's asymptotically non-decreasing. I'm not going to give you what n0 is just because I think it complicates the proof a little further. So let me just do this right here. Why? Because I'm going to give you more constants. I don't want to give you even more that I don't need. The point is that it's asymptotically non-decreasing, so there's going to exist a certain constant such that this inequality is going to hold. Since now I'm going to justify this. Now remember, this really just means that the input in here has to be less than or equal to whatever's the input in here. So I'm just going to do a little algebra here. Since k plus 1 is less than or equal to 2k, would imply, well, if this is true, if and only if, I'm just going to do some little algebra. I'm going to subtract 2k for both sides of the inequality. Would imply these two are logically equivalent statements. And then what I'm going to do is I'm just going to simplify this. You'll notice I have 2k minus a k, so it means that's a k. But then that means I'm subtracting off 1. So that means that this is true if and only if k minus 1 is greater or equal to 0. So this statement is true for all k greater or equal to 2. So I just need the care that it's greater or equal to 2. Remember, in the induction, k is greater or equal to 2. So I just want to make sure this holds for k is greater or equal to 2, because k minus 1, if you put 2 in here, for example, you get 2 minus 1, which is 1, that's greater or equal to 0. I just want to make sure that this is true for all sufficient k, which we define k to be greater or equal to 2, right? So I'm going to invoke smoothness here. Then, by the smoothness of f, let me put f right here. Then by the smoothness of f, we get the following property. F of k plus 1 times n is less than or equal to f of 2kn, right? Because it's asymptotically non-decreasing. We know this inequality is going to hold for a sufficient value of n, which means that there exists an n0, right? Such that this is going to work. But now this is where I'm going to get a little slick here. So just read this very carefully. You'd agree with me that this right here, I'm going to rearrange the terms in here. I'm just going to associate them a little differently. So this would be equal to f of 2 times kn, or these are in parentheses, right? This is no different than this. But what does that mean? Well, if I have f of 2 times a something, and this is the input here to this, so this should look really strange, a little familiar to you. So I have 2 times a something inside the f. And I know that f is smooth, right? I know f is smooth. So what I'm going to do is I'm going to drop the 2, because it's 2 times input, 2 times the input. And this input is just it's k times n. But what does that mean? Well, it just means this. It just means that this 2, so f of 2 times k times n together, I can drop the 2 because of it being smooth. So I get this. Do you see what this? So this is a very slick little trick I've just performed here. So if it's really hard for you to see, just imagine I put another variable right here. Just imagine this was like m or something, 2 times m. I'm just going to drop the 2, and then I end up with just k times n, or just m. Okay? So that's just what I'm doing here. So that's how I'm using smoothness here. So now, once I have that, you'll realize very quickly that all I really need to do now is somehow connect this up with what's over there. So what does this mean? So what does this mean now, this whole chain here I have here going? It's implying there exists constants C1, which is a positive real number, and N1, so N sub 1, which is a positive integer. So it's positive real, positive integer. I'm just invoking the definition of big O, because I know that this relationship holds. So I'm going to pick out those 2 constants that represent this relationship. So I'm going to pick C and N0 such that this holds. Such that this holds. Such that what? Such that for all n greater or equal to n sub 1, f of k plus 1 times n is less than or equal to c1 times f of k times n. Right, that's just the last part of my setup here. Do you see that? So I'm just using the last part of way over on the right. I'm just using that. I need the big dramatic stick to do this, okay? So let's. So what are we going to do here? Well, now I have these C1 and an N1. What have I not used yet? I haven't used the induction hypothesis, right? I had it over here on the left here. I have it on the left. So what do I need to do next? I need to invoke that. By the induction hypothesis, we know already that f of k times n is big O of f of n. So there exists constants. So remember, I'm just using the big O definition again. So there exists, sorry, my writing's melting in the microwave again. So there exists constants, C2, which is a positive real number, and N2, which is a positive integer, such that what? I'll just rewrite this a little differently. Don't want to bore the reader too much. Where f of k times n is less than or equal to C2 times f of n holds for all n greater or equal to n2. So you notice I'm just invoking the big O definition a couple of times, right? So just to walk you through this step here. So remember, up here, all I've done is I've used this inequality to get me to the property where I could invoke smoothness. So that's how I get that big O relationship where I'm saying f of 2 times kn is in big O of f times kn. So I've dropped the 2 there. That's from smoothness. Then what I did is I used the fact that f of 2 times kn is big O of f of k times n to get these 2 constants, C1 and N1. And then what I do is I use the induction hypothesis to get C2 and N2. So now I'm going to just use those and connect those up, okay? So that's going to be our goal here. So we already have N1 and N2. We have C1 and C2. what I want to do is I want to bring those two together and then try to give you something that looks like a big O statement again, because that's really what B of k plus 1 is, right? So I'm going to select constants now. By selecting constants, C is equal to C1 times C2, and N0, which is going to be equal to the maximum of N1 and N2. Now, you might ask, Dan, how do you know that these are going to be big enough? Now, remember earlier I said there's some sufficiently large N that inequality that I originally had would work. Now, remember that I was using as a little point to get me to the big O relationship that I did get N1 out of. So I'm using that N1 because I know that that inequality will anyways work for this sufficiently large one, because I already know that it holds for the one I really want to prove. So remember that the equality I had at the end, where I have the big O relationship that I get N1 from, it has to also be true for f of k plus 1 times n. So it has to be true also there. So that's why I didn't give you a constant when I invoked the asymptotically non-decreasing property at the beginning of our inductive step. So that's why these two are okay. And I just need to pick the larger of these two because they need to just be big enough that I can do the algebra properly. So then I could say this. Then f of k plus 1 times n is less than or equal to c times f of n. It holds for all n greater or equal to n0, which is b of k plus 1, right? Well, that's what we need the proof for the induction step. We need to find c and n0. But we did, we put the two pieces together that got us to the right spot. Why? Why? Let's think about this. Let's think about this. Let's think about it. Let's go back over here. I want us to do this more slowly here, because I know some students might lose me here. Because where did that come from? Well, let's think about this. Let's think about it. Okay. I'm pulling this back over here. We're going on an adventure, guys. Okay, so let's just try this. Okay, so I want to pull this back over here. So remember, what we want to prove is this. We want to prove that f of k plus 1 times n is big O of f of n. So we already have two pieces here, right? The first one is we invoke the smoothness and we get that relationship over there. The f of 2 times kn is big O of fkn, right? F of kn. So we get these two constants here. They get us to this point right here, right? We get f of k plus 1 times n is less or equal to c1 times f of k times n, right? Well, by the inductive hypothesis, we also get that f of k times n is less or equal to c2 times f of n, right? So what we'd like to do is some way of getting us from here. Sorry, we want to go from there to here to get to f of n, right? So how do we do that? Well, you would agree with me that probably that I can go from, we'll see this actually in another proof I'll be doing involving smoothness exactly. So I have this times is less or equal to c1 times f of kn. You'd agree with me that this should also be less than or equal to c1 times f of kn. But you already know that if I put c1 right here, that means c1 else has to go right there, right? That's where c comes from. I end up with c1 times c2 times f of n. And that's where c comes from in the proof here. So hopefully that clarifies why we picked c and n0 the way we did. So now that I have this, so I proved the induction step here. So what are we going to do? We got to invoke the principle of mathematical induction. Therefore, Therefore, by the principle of mathematical induction, B of B is true for all B greater or equal to 2. And we're done. So this proof is a little tricky because I use smooth this a couple of times. Once in the base step, one in the induction step, right? The whole idea is that I use smoothness to drop out a factor of 2. And I get that factor of 2 from the fact that it's asymptotically non-decreasing. So I pick a sufficiently large constant for the n0 so that I can form a chain of inequalities that gets me from here. So if you want to just see what I mean, you would have it where, let me just write it out for you. That way you can see quite quickly. So I have this, and you agree with me that this is less than or equal to C1 times f of kn, right? And we know this is at least for n1, right? But we also know that f of kn is less than or equal to f of n for some c2 such that it's n2, right? So I'm just invoking the existence of n1 and n2 to get either one of these two separately. So what I want to do is I want to make this continue along. I'm going to make it so I invoke what some people call transitivity. So you'd agree with me that if I wrote this, you'd agree with me that I could get, so if I put C1 right here, I could also put C1 also here on this side for a sufficiently large value of n. So that's what I'm going to do. So I just simply do this. So you'd agree with me that I could just simply go, this is less or equal to C1 times f of n. So I'm going to put C1 times C2 times f of n. And then you end up with this being equal to C1 times C2 times f of n. Sorry, my f of n is sort of dying there. F of n, and this is just C right here. That's where it came from. In my notes, I actually have two alternate proofs. One showing you the versatility of big O notation when you use the equals-like notation, which remember isn't equality. One version of that, and then another that uses this property, so-called the transitive property of big O. So I have two different versions of this that I do argue that are much simpler than the one I've just presented to you. So if you want to take a look at that, take a look at my notes, okay? So I want to say thank you very much. Have yourself a beautiful day.